Okay. Now see the multiplication theorem of probability. This is also known as theorem of compound probability. The theorem states that if A and B are any two events, then probability A intersection B equals to probability A into probability B given A, and of course probability of A greater than 0. And this can also be written as, if we just interchange A and B, so we can write probability B into probability A given B, and at that time probability B greater than 0. We can get this statement from the definition of conditional probability also. And you know what is P B given A and what is P A given B. The proof is very simple. We just apply the set theoretic definition. Probability A equals to number of elements in the event A divided by number of elements in the sample space S. Similarly, PB equals to NB upon NS, and PA intersection B equals to NA intersection B divided by NS. Now for conditional event A given B, as I have explained through one example, for this conditional event A given B, the sample space is B, and the number of favorable outcomes becomes the number of outcomes in A intersection B. I have explained this already through one example. So PA given B equals to number of outcomes in A intersection B, or number of elements in A intersection B divided by number of elements in B. And I tell you again that for conditional probability, or for conditional event A given B, the sample space becomes B, and for the conditional event B given A, the sample space becomes A. Now if you rewrite this PA intersection B equals to NA intersection B divided by NS, if we rewrite this as NB upon NS into NA intersection B by NB, NB and B gets cancelled, so we can rewrite this way. So what is this NB upon NS? This is nothing but PB. And what is this? NA intersection B upon NB? This is B A given B. Similarly, we can rewrite this star, that means probability A intersection B, as this way also. And what is this NA upon NS? This is PA, and NA intersection B upon NA, this is PB given A. Now one interesting thing is that if A and B are mutually exclusive, if A and B are independent, then what happens? If the events are independent, then the conditional probability becomes equal to the unconditional probability. So PB given A becomes equals to PB, and PA given B becomes equals to PA. So if A and B are independent, then PA intersection B equals to PA into PB. This is the multiplication theorem for independent events. If A and B are two events with positive probabilities, that means PA not equal to 0, PB not equal to 0, then A and B are independent if and only if PA intersection B equals to PA into PB. Fine. We should know this definition: pairwise independent and mutually independent events. Suppose n events are there, a1, a2 up to n, and these n events are said to be pairwise independent if every pair of these events are independent. If every pair of these events are independent. That means a1 and a2 are independent, a1 and a3 are independent, a2 and a3 are independent, a4 and a5 are independent. In this way, if every pair of these events are independent. For example, if three events are there, A, B, C, then they are independent, they are pairwise independent if A and B are independent. So when A and B are independent, if PA intersection B equals to PA into PB. A and C are independent, B and C are independent. And what is mutually independent events? The events A1, A2 up to An are said to be mutually independent or simply independent if probability of joint occurrence of any number of these events is equal to the product of their probability. So simply say that A1, A2 and An are mutually independent or simply independent if A1 and A2 are independent, A1 and A3 are independent, A2 and A3 are independent. In this way, every pair is independent. Again we say that A1, A2 and A3 independent, A2, A3, A4 are independent. That means every triplet are independent. So for an example, A, B, C are said to be mutually independent if A and B are independent, A and C are independent, B and C are independent, A, B, C are also independent. And when A, B, C will be independent, PA intersection B intersection C equals to PA into PB into CC. But in case of pairwise independent, what happens? Every pair of events are independent. If four events are given, A, B, C, D, then when they will be mutually independent, if A and B are independent, A and C are independent, A and D are independent, BC independent, BD independent, then CD independent, then ABC independent, then ACD independent, BCD independent. In this way, ABCD all are independent. This is called the mutually independent or simply independent.